Hello everyone. What we've got here is a DC drive. There's no data plate on it, so I had to reverse engineer the inputs and outputs. I'll show you that at the end of the video. On the front of the drive it says RE. That's all I know about it. I've got a DC motor over here with a tach. The tach output, this is a 90 volt DC motor. The tach output is 7 volts DC per 1000 RPM. Over here is a 3-phase variac, 3-phase transformer. That allows me to adjust this AC coming into the DC drive to power it up. This bus cap right here is a 250 volt DC bus cap, 270 microfarad. So I knew I wasn't going to be putting 220 volts AC into that drive, so I had to sneak up on it. And at around 50, 60 volts, the green OK light come on. And I brought the remaining bus voltage, I brought it up to 90 volts DC, so we'd have 90 volts DC for this motor right here. But this knob right here adjusts it, so you can adjust the AC going into that drive. Well, let's fire it up, see what it does. It's a servo drive, a DC servo. So I've got the tach output going into this connector right here, an enable, and a speed paw. I'll show you all these hookups at the end of the video. Let's go. We just enabled it with this switch right here. Speed the motor up. Slow it down with the potentiometer, go back the other way. Now these 3 red wires, that's the 3-phase AC going into the drive to power it up. These 2 white wires are the motor. Here we got a blue and black wire, that's the tach generator, tachometer generator. Let's go look at the waveforms going out to that motor with this oscilloscope. I'm going to move the camera closer so y'all can see the motor waveforms. Give me a bit to move the camera. Let me turn this back on. That's fascinating. Now, notice that most of our pulses, I'm going to speed the motor up. Most of our pulses to run that drive are up here on the high side. Now, right now, the motor is running clockwise, as viewed, looking into the shaft of the motor. Now let's go the other way. Let's go counterclockwise. Now we're moving counterclockwise. Now look at that. Most of the pulses are down here on the negative side. The middle here is ground. Let's go back the other way. That's fascinating. It is fascinating that you can take these square wave pulses and run that motor, that DC motor. I notice that the amplitude, the peak amplitude of those square waves does not change, but it's the width of the pulse that changes to make it run faster. Now it looks cleaner down here because we're triggering on that one pulse right there. If I move the triggering point down here, then the top side would look like this. We just went unstable right there. Let me move that triggering point. Move that triggering point down so it's below ground. There you go. The triggering point's right here on this one negative going pulse. And you see how it cleaned up that top side. That is amazing. That's 50 volts up here, 50 volts per division. So we have almost 2 divisions, and that's our 90 volts peak up there. And it's 50 volts per division down here, and so that's negative 90 volts peak down here. We're almost covering 2 divisions up here on the positive side and 2 divisions on the bottom, so we're close to 100 volts. Now right here, you see the peak is almost at 100 volts, but we know it can't peak out at 100 because our DC bus voltage is 90 volts DC. Down here on the negative side, we're almost at 100 volts also, but that's a negative 90 volts peak on the bottom side. We're just creeping along right now in the clockwise direction. And right there we're stopped. Well, not quite. Right there we're stopped, and look, we have an equal number of high side and low side firing there. Now we're going in the counterclockwise direction again. Let me move that triggering point positive again, so it'll look a little bit cleaner on the negative side. There we go. Now we're triggering on this one positive peak right here, this positive going waveform. Isn't that neat how you can take a square wave like that and run a DC motor? That is fascinating. Okay, we're done here. Let me put the lid on it. When I get to the house, I'll show you my drawings. Let me stop that motor. I'm going to speed it up with the potentiometer. Now let's go counterclockwise. We'll disable the drive. Alright folks, stay with me. We'll take a look at the drawings I made of this drive so I can figure out how to run it. See you in a little bit. Hello everyone. Now there's sometimes when you get an item in the shop and you don't know how to run it or power it up, you have to pull out the pencil, paper, and the meter and figure it out, because you won't always get schematics. Well, no, I take that back. You'll never get schematics. Schematics have been long gone since the days of tube TV sets. So, I remember, I'm going to get sidetracked here. I remember when I was a boy, my dad could pull the back of the TV set, the panel off the back of the TV set, and there was a schematic showing all the tube connections. Okay, so back to our drive. This is the RE drive. I have no documentation on it. There's no data plate on the drive. I don't know how much voltage to power this thing up with. All this had to come from experimentation. So this right here is the green connector on the side of the drive. This is the control connector. So I mapped out all 16 pins of that connector. I didn't go all the way in. You'll notice here this operational amplifier stops right here. All I wanted to do was to figure out whether I had an output or an input, and then based on my drawings I could make some educated assumptions or educated guesses about what this input is supposed to be doing. So let's start here at pin 1 and 2. We have an output from an optocoupler. This optocoupler here could be an alarm output or drive ready. So here we got an output. I'm not worried about that right now. I want to figure out how to make this drive run that DC motor. That's all we're worried about. Now here I mapped into an analog circuit. This is analog input. This could be our speed reference. We might have to put a pot right here and its wings to a plus and minus voltage, maybe from an external power supply or an internal supply from the drive. I don't know yet. We'll move on. We just go far enough in to find out whether it's a digital output or an analog input or a digital input or an optocoupler input. We want to know who the inputs and outputs of this connector are. Now here on pin 4 we have the drain of a MOSFET connected to pin 4 through a 47 ohm resistor. So that's an output. Not sure what it is. Could be anything. Could be this is the ready output and that's the alarm output. Not really sure yet. Now here I've got a Zener diode in parallel to 18 k ohms to ground, and then a forward bias diode. So this is a voltage output. And it's right beside pin 4. And right beside pin 6, of course. So maybe this DC volt out is for the supply of this right here. Maybe this is supposed to be turning something on, like maybe an external relay or something like that. I don't know. So here we've got that first 5 pins. Now let's go look at the next few pins of that green Phoenix connector. Look at this. I mapped this. This is odd right here. And what's really strange is that when I put my meter on here to ground, I had a negative 11.13 volts DC. Negative right here. But this AND gate, this HEF 4081 BP, This ground pin's not tied negative. Its ground pin goes to supply ground. Okay, so anyways, we know that this is now an input. This is an input going to pin 1 of that AND gate. Pin 2 of the AND gate I never mapped out. I was going to map it out, but I never did. So let's come down here to pin 7. I measured through here when I powered up the drive, 19.23 volts DC, close to 20 volts DC right there. On pin 8, there's no wires, so I've got no connection right here, NC. Now this got really weird. This took me a little while to figure this out, and through experimentation I figured out that that was the tack input. One end of the tack goes in here, but look at this. If I close switches 1 and 2, these are the dip switches back up here. You see these up here beside pin 1, there's 2 dip switches. That's these 2 dip switches right here. If I got a low voltage tack, I close these 2 dip switches right here. And in fact, the tack on the back of the motor that I was using, it's 7 volts DC per 1000 RPM of that motor. So I've got a low voltage tack. If I got, say, a 40 volt or a 50 volt tack, then I would open up one of these dip switches and that voltage would go through here. It wouldn't matter which one I opened up, either one. If I had, say, a 80 to 100 volt tack, I would open up both dip switches and the voltage would go through that 10K and then that 10K and then on into the circuit. I didn't draw the circuit out, but I know that this Vmax potentiometer goes to pin 2 of a TL084 operational amplifier. There's that circuit right there. We'll come back to these in a little bit. Now, here's the other side of the tack. And I'm telling you, I had to guess, because this could be an analog speed reference in, but going back to these dip switches, you don't select voltages for analog speed reference in, but you do for tack. Let's get that out of the way. I'm jumping back and forth here. So here's the other side of the tack, going through a 22 kilo ohm resistor and some more resistance and capacitance, filtering to ground and whatnot. It went to pin 3 of that same TL084 CN that this Vmax pot went to. So I knew that 9 and 10 were the same function because they went to the same operational amplifier, pins 2 and 3. Now pin 11 is frame ground. That grounds that drive to the frame of the machine. Now here is where I found the problem to that drive. The problem with the drive is that the speed reference would not cause, when the customer increased the speed reference into that drive, the motor didn't move. The motor did not move. But here's the problem I found. There was a scorched trace from pin 12 to ground of the power supply of that drive. Now someone had replaced that wire, but it come undone again. And so I took the repair off, the previous repair off, and repaired it again. And that brought the drive back to life. I could run it back and forth with the speed potentiometer. That was the problem, right there. The previous repair had come undone. I knew when I mapped this circuit out right here, I knew that this was the speed reference into the drive to make that motor run clockwise, counterclockwise, fast and slow. I knew just looking at this because I'd seen this circuit hundreds of times in the past when working out how drives run. But another reason, and I'm going to show you, let me get that pin 12 ground back up here, the one that I had to fix. Let me get this back up here. Look at the grouping, look at the function. I've mapped out this circuit down here. We had these circuits up here mapped, and we'll map that out. But look at this. Pin 13 is going into the inverting input of that operational amplifier. Pin 14 is going into the non-inverting input of that operational amplifier. Here's pin 12 is ground. 15 has a 10 volt zener out here going to negative 15, so I had negative 10 volts DC out here. Pin 16 was going to a 10 volt zener circuit right there, each having 470 ohms, and the 16 going up to 15, so 15 volts DC. So 16 had plus 10 volts DC right here. 15 had minus 10 volts DC right here. You could put the wings of your potentiometer right there. The wiper of the potentiometer would only have to go this short distance. And then on 14 or 13, it don't matter. You could ground 13 to 12 and run the wiper into 14, and you'd be good to go. You'd be running. You'd tell that drive to run clockwise or counterclockwise. So, with these all side by side, I could make the correct assumption that this was the analog speed reference in. Let's go back a little bit and talk about the digital input. Here we have one digital input. That has to be the enable, the input that makes this drive run, the input that makes this drive get up and go. But what do I put into it? If we go back here, you remember I said that 5 was by 6, and I had, let's go over here. Can y'all see that? Let me don't run it off the paper there. On 5 I had 9.64 volts DC coming out. That might have well been 10 volts. Could I run that 10 volts into pin 6 and enable that drive to run? Well, I tried it, and nothing happened. But when I ran pin 7, the 20 volts DC, the 19.23 volts DC into pin 6, that drive got up and went. So you have to do a little bit of experimentation. Just like I had to experiment with the TAC input. Just looking at other drives, I knew that seeing these current limiting selections that I could make allowed me to select a TAC from, I don't know, close both of them, 0 to 20 volt TAC, open up one of them, maybe a 50 volt TAC, open up both of them, and a 100 volt, maybe 80 volt TAC. You see how that works? And that's how I figured out how to make this drive run, was by drawing all of these inputs and outputs. Digital in, digital out, analog in, analog out. It gets tedious, but if you want to know if that drive works, well, that's how you do it. It's a little insane. Now, let's move that out of the way, and we're going to take a little bit of a break. Got to catch my wind. I talk too much, but that's how you learn. And we're going to look at the power section. I got 2 drawings of the power section, and we're going to look at that. Okay. I'll see you in a little bit. Okay, we're back. Here is the three-phase bridge rectifier circuit that makes the DC bus to run that motor. We have R, comes in on pin 1 and 2 of the front connector. S comes in on pins 3 and 4. T comes in on pins 5 and 6. That AC waveform gets rectified to a DC voltage by these 6 diodes. That rectified DC voltage gets filtered, gets smoothed out by this 270 microfarad 250 volt capacitor. Now, I wanted to run a 90 volt DC motor, so I crept up, I sneaked up on RS and T with a variac until I had 90 volts DC across this capacitor right here, the plus bus and bus ground. There's a formula where you can figure it out. Let me bring this calculator in here, see if y'all can see that. I'll get closer, give me a little bit. Okay, let me see if I can reach around that camera and push these buttons. So we have 90 volts DC divided by the square root of 2. The square root of 2 is 1.414. That gives us an AC voltage of 63.64 volts AC, 3-phase, to give us 90 volts DC on the bus and bus ground there. Now that's well below that 250 volt DC capacitor. We have no fear of getting close to damaging that capacitor. Here's the power section that runs the motor. Up here is plus bus and bus ground. Plus bus goes to the drain of these two MOSFETs. Bus ground goes to the source of these two MOSFETs. Now, the source of this top MOSFET is connected to the drain of this bottom MOSFET, and the same over here. Source to drain. The motor is connected between these MOSFET pairs. This connector right here is the same connector that we brought the 60 volts AC or thereabouts, very close to RS and T, the line voltage coming in. Here M1 is connected to 7 and 8, pins 7 and 8. M2 is connected to pins 9 and 10. There's our motor. That's our armature for that DC motor. It connects to these pins right here. If we want to run clockwise, we'll turn these two off and these two on, and now current flows through this power MOSFET, through the motor, through this MOSFET, and back out to bus ground. Notice we were going in this direction. Current was flowing in this direction. Now if we want to run the other way, what do? Well, let's turn those off and we'll turn these two on. And now current flows through this MOSFET, through the armature in this opposite direction, through this MOSFET, back to bus ground. Isn't that amazing? Now, these MOSFETs are not continuously turned on. They're pulsed, as we saw in the oscilloscope waveforms when we were looking at these 2 points right here with the fluke oscilloscope. We saw that they were being pulsed on and off. That reduces the workload of these two MOSFETs here and these two MOSFETs here. That reduces the workload. If you if you were to continuously turn these on, they would overheat. They would overheat and die. They wouldn't last as long as when you pulse these on. Another thing that we run into is when these two right here are turned on at the same time. If you looked, and that's when you get the MOSFETs are blown open for some reason in the firing channel. This device right here, or this device right here, was left on when we started firing this device right here. Say the gate firing channel of that MOSFET right there failed, and this MOSFET was turned on all the time, and then we went to go turn this one on right here. Well, what happens is when you do that, you got both MOSFETs on at the same time, and you have full current from the DC bus through both these, and that's basically a short from plus bus to bus ground. And things just come undone very quickly. Oh yeah, that's a lot of current through here when you short plus bus to bus ground. Those power MOSFETs, they can handle a lot, but they can't handle them types of currents. We exceed the maximum current rating of those devices very quickly when we've got both these turned on. Makes for a mess, and that mess is hard to clean up. Okay, now let's look at my hookups. Let me get the camera oriented so you can look at these hookups right here. Here they are. Now you'll notice that I've only connected enough to this drive to make it run. Here's that pin 6 digital input, and here's that near 20 volts DC. I put a switch out here. That switch connects that plus 20 volts DC to that digital input and makes that drive get up and go. Here's the TAC input on 9 and 10. There's my TAC generator. That TAC generator is on the rear end of that DC motor. I've grounded the ref inverting input to pin 12 ground. I've got the wiper of that potentiometer. This is what I'm changing direction and speeding the motor up and down with, this potentiometer right here. I used a 10K, 10 kilo ohm potentiometer works. And I've got the wiper going to pin 14. That's the reference non-inverting input to that operational amplifier. Here's that plus or minus 10 volts DC. They're on the wings of the potentiometer right there. That gives you a speed reference on 14 of plus or minus 10 volts DC. Up here is where the motor connects. There's M1 and M1 on 7 and 8, and M2 and M2 on 9 and 10. Let's go look at R, S, and T in that variac. Now I've got a 3-phase variac right here. That's a 3-phase transformer that you can adjust the output. Here's the output side. This is the input side. I got 220 volts AC, 3-phase coming into the input of that transformer. And on the output, I adjusted it with that knob so that I had about 60 volts 3-phase AC coming into the drive. That gave me about a 90 volt DC bus voltage. I used this variac to sneak up on that drive because I wasn't sure what to put into it, but I knew I needed at least 90 volts for that 90 volt DC motor. Always make sure that you got this turned all the way down when you're sneaking up on something. You don't want to start out too high and blow that 250 volt bus capacitor by overvolting it. Well, there you go, folks. There you go. I hope you enjoyed that video. I hope it helps you to see that you can start from an unknown and work your way into a running product. That was a lot of fun. I mean, it really was a lot of fun because we were going from something that we didn't know, had no idea, and we ended up with a running DC servo drive. Isn't that amazing? All right. Okay. Thank you very much for stopping by, folks. I always enjoy it when you come over. We'll see you next time.